We begin this third chapter of notes that describes the battery state estimation. So let's think about that a little bit. And this topic we're addressing right now is all about definitions and preparing the background to do battery state estimation. We've seen already in chapter 1, when we looked at the functions of a battery management system, that one of the important functions is to be able to estimate certain quantities that are cell related in the battery pack that somehow describe the battery pack condition, but for which we have no means of measuring them directly. So we have to somehow take some direct measurements of some physical quantities and perform calculations or inferences or estimates or something to get the desired estimate of this description of present battery pack condition. In this chapter, we do something called battery state estimation, and next chapter we do something called battery health estimation, which is also properly battery parameter estimation. So I want to make a distinguishing difference between what I mean by states and parameters. A state of a dynamic system is something that I think about as a quantity that describes the entire past somehow that brought us to the present state. I can't define it without using state, but the present state of the cell. So that if I wanted to be able to predict the future, I don't need the past, I need only the state. The state variable describes the impact of the past sufficiently well that I can predict the future if I know only the state and the future input. States are things that can change quickly and tend to change relatively quickly. And if you want to have something a bit more concrete, if we look at our enhanced self-correcting circuit model, inside that model we've got a state vector xk, and inside of that state vector we have the state of charge, we have the diffusion voltages or currents, and we have the hysteresis voltage. Any of those I would think of as states. State of charge can change its entire range over the course of several minutes, depending how the battery pack is operated, as can the others, diffusion voltages and hysteresis voltages. Parameters, on the other hand, the biggest difference between a parameter and a state is the time scale of variation. A parameter changes slowly. In fact, you might just start out by saying a parameter never changes, although that's not strictly true. So we could say in a very well-maintained battery pack, the cell capacity will change only a few percent over the course of many years. So maybe over its lifetime of 10 to 15 years, we might lose only 30% capacity. So only a couple percent capacity loss per year would be expected. Much slower rate of change than states that can change in minutes. We're talking here years, orders of magnitude difference. Similarly, resistances of a battery pack, the ability to deliver power, in other words, would change slowly over the course of years rather than minutes. So parameters tend to change due to aging, due to degradation. And if they were to change quickly, that would be to some kind of terrible abuse. But under normal operating conditions, we would not expect them to change rapidly at all. So in some models, we might just say the parameters are constant. But if we want our models to be accurate over the lifetime of the battery pack, we would acknowledge that they are in fact not completely constant, and we would want to be able to adapt the parameter values as well. In Chapter 4, we'll look more at adapting parameter values, but here in Chapter 3, our focus is on how do we infer the state of a battery cell based only on measurements that we know how to take, such as voltage and current and temperature of the cell. I think for the first time we're seeing this schematic diagram. And I prepared this diagram as an illustration of the topics of this course. And we'll refer back to it now frequently, every chapter, to give us an idea of the progress that we are making as we understand all of the concepts, as we learn the concepts of battery management algorithms for control. The program loop of a battery management system does any number of things, and we've seen quite a number of things in Chapter 1 that I said I would only touch on fairly superficially. So everything in Chapter 1 we have to do as well, but these icons here and these steps are the more control-oriented steps of a battery system, and these are the ones that are the real focus of this course. When we turn the battery pack on, I use the term key on because I'm thinking of an automotive application, but that's not necessarily the case. We will initialize our algorithms. And then we will enter a program loop which comprises all of these steps that are outlined. And we will do one of each of these per measurement interval. And so we're doing these over and over and over again, maybe once per second if you just want a number to put in your head. Might be the rate at which we are doing these. So every measurement interval we are going to measure voltage and current and temperature. And these are topics that we talked about in Chapter 1, so we're not going to go back to those right now. We're going to use those measurements of voltage, current, and temperature to estimate the battery state. And one element of the battery state that is pretty important is state of charge, although I would argue that all elements of battery state can be important as well. So in this chapter, in Chapter 3, we address estimating battery state, including but not only state of charge. Then we would like to estimate some indicators of battery health. And those might be an indicator of how much capacity has degraded or how much resistance has increased, or perhaps even other things different from that. We're estimating parameters, really, of the battery cell models. And these are things we will address in Chapter 4. Battery cells can become out of balance. Different cells may over time develop different states of charge from each other, and that will limit the ability of the battery pack to perform its function. And we need circuitry and methods to bring the battery cells back into balance. And this is the topic of Chapter 5. And we've already seen actually how to compute battery pack energy limits, and that was back in Chapter 1. It was fairly simple. We actually don't have to go back and revise any of that. But we looked at a very simple method only in Chapter 1 for computing battery pack power that can be greatly improved upon. And in Chapters 6 and 7, we're going to look at those ideas of different ways of computing power limits for the battery pack. So this is how the course is structured. That's why this iconic figure is important to me, to let us take stock of where we've been and where we're going. Chapter 1, we've already seen that, and Chapter 2 on modeling and simulation was also good review and background material. Right now we're in Chapter 3, and the heart of this course is in Chapters 3 and Chapters 4. If you go back to the syllabus and count up the number of estimated weeks for these topics, I believe this is about half of the course is going to be spent in these two major sections. The vehicle will operate, the battery pack will operate, every measurement interval will measure, will estimate state of charge, state of health, will balance, will compute power limits, will repeat over and over and over again. At some point, the battery pack is turned off. It's disconnected from the load, so we have a power down process. And usually we'll want to be able to store some information from what we have learned while the battery pack was operating. For example, the state of charge changed, so I might want to store that in a memory location. So next time I turn on the battery pack and initialize, I can pick up where I left off with that previous state of charge. But more than that, there's these long-term aging things that evolve so slowly over time that it's really hard to estimate them quickly. It's hard to get a really good capacity estimate over a brief interval of time, so I'll want to store some data of what I've learned about cell capacity during this interval that the battery pack was turned on, so that I can then reload that information and pick up where I left off next time the battery pack is being used. So there's any number of any amount of data that you might want to store. That's up to the user decision, but I indicate there that you probably want to store something. So hopefully this milestone chart will be helpful to you to think of how the course is organized. When we estimate the state of a cell, one thing that we're going to be interested in is the state of charge of a cell. You've seen this before in the enhanced self-correcting cell model. It's the variable z, so z at time k. And even in chapter 1, we made a connection between the electrochemical model parameters and the z sub k. So we have some idea electrochemically of what state of charge is. We have some experience of using it in a model. When we're doing simulation, we know what state of charge is because it's inside of our simulator. We're actually updating it every time sample, and so we can use that variable in our program to know state of charge and to do things with it. But inside of an actual battery pack, we don't have the ability to measure state of charge. And it's important to have an idea of what state of charge might be, because the variable is an input to how we balance cells, how we compute the available energy, and how we compute the available power of a battery pack. So even though I think it's important to be able to estimate the entire battery model state for reasons that will become more evident in Chapter 6, here our focus is going to be on estimating state of charge only. We'll look at some simple methods that you can write in code in minutes, literally minutes. They're not hard at all, but they have some significant problems to them. They're not robust, and there will be a homework set where you will evaluate and examine some of these simple methods and be able to explore, what are their strengths and what are their weaknesses. We're going to spend the majority of this chapter looking at some more advanced methods that can estimate the entire battery model state, including state of charge, but not only state of charge. And since they actually measure the whole state, or estimate the whole state, that allows us to do some more advanced things with the estimates in Chapter 6 rather than just relying on state of charge only. But there's actually a fair amount of background material that we have to develop before we can examine these advanced methods. And so we'll take our time. That's why this chapter is one of the longer ones, to step by step lay the foundation to be able to understand the state of charge estimation methods that, to my knowledge, are the ones that work the best at this point in history. State of charge. What is state of charge? Well, it's something like a dashboard fuel gauge. It reports a value from empty, notionally empty, which we would report as 0% state of charge, and notionally full, which we would report as 100% state of charge. In a gas vehicle, there is a fuel tank, and there's a way to pretty much directly measure the gasoline level in the tank, essentially just putting a float in the tank and measuring the height of the float. But but there's no such sensor available to measure state of charge. I can't put a float in a battery cell and somehow measure the height of the float. There's no physical analog. There are some research teams that are looking at very clever ways to implant different types of sensing tools inside of battery cells, but I haven't seen yet any really good results. Now, it's possible that 5 years from now, 10 years from now, someone will come up with a solution and where you can measure state of charge directly. And if so, I would say, great, that's fantastic, because one of the things you learn when you study estimation is you never want to estimate something that you know. It just doesn't make sense. You introduce errors when you're estimating things that you don't have to introduce if you can measure them and know them directly. So for the time being in history, and as far as I can see for the foreseeable future, there's not going to be any sensor implanted in a battery cell that will be able to measure the state of charge directly, certainly not in battery cells that are production ready. Maybe there's some lab devices out there, but nothing that's ready to go to full scale and go into production. So we need a way to, instead of measuring state of charge, estimate state of charge from other measurements. Say, well, why? Let's have some motivation. So I tried to put some ideas up front of motivating why state of charge might be valuable, to have it, especially not only state of charge, like some wild guess, but a good guess, a good estimate, a precise estimate, an accurate estimate. Maybe accurate is a better word than precise here. One of them would have to do with longevity. And I'm comparing all along with the idea of fuel in a gas tank and charge in a battery. So fuel in a gas tank, if I put too much fuel in, it doesn't hurt the tank. Some of it spills, and it hurts the environment maybe, but it doesn't hurt the tank. If I empty the gas tank and there's no fuel left, it doesn't really hurt the tank. The tank is fine. My car stops. It may be a challenge to get the car started again, but the gas tank itself is fine. The battery is not like that. If I overcharge a battery by putting too much charge in it, that's going to cause permanent damage. It will reduce the lifetime of the battery cell, and it can even be catastrophic, resulting in fire, for example. Overcharging is something we never want to do. Over-discharging is also a problem. It's going to cause damage as well. If we over-discharge quickly, it tends to cause more permanent damage than if we over-discharge slowly. However, in either case, there is the possibility of permanent damage. So it's different from a gas tank. We need a precise, accurate state of charge estimate to help us monitor the the status of every cell to make sure that we don't overcharge or over-discharge any of the cells in the battery pack. Performance. So suppose I know that my state of charge estimator is not that good, but maybe it's the best I know how to do or the best that I'm willing to implement because I don't want to spend the time to do something that's better. So what am I going to do? If I know my state of charge estimator is bad, not bad, but poor, then I have to be very conservative when I use the battery pack to avoid overcharge and over-discharge situations that might happen if I believed an estimate that was in fact wrong. So if I say in my battery pack I'm allowed to use between 0% and 100%, and that might not be the case, but let's suppose we are, and I know that my estimator has an error bounds on it of plus minus 5%, and if I knew that exactly, then I would never charge my battery pack to the point where any cell was above what I thought was 95% because I've got to leave this 5% margin here to make sure I'm not overcharging a cell by mistake. Similarly, I would never discharge a battery pack beyond the point where any cell was at 5% because my margin of error says if I discharge a cell farther than that, it may result in an undercharged battery cell. So if I've got an SOC estimator with error bounds of 5%, I can use only 90% of the capacity of the battery pack at most. If I have an estimator with error bounds of plus minus 1%, then I can use 98% of the capacity. So 90 versus 98. That's a pretty significant difference. It's almost a 10% difference, and we could make it 10%, I suppose, by making that plus minus 6. 10% of thousands of dollars is hundreds of dollars. So if I'm wasting 10% of the capacity of something that costs thousands of dollars, I'm actually wasting hundreds of dollars. And that can be a differentiator, at least in a profit margin differentiator or maybe even a sales differentiator between one product and another product. So that's pretty important. So if I have a good estimate, one that I know is good because it has known error bounds, then I can aggressively use the pack capacity. If I have a poor estimator and I happen to know its error bounds, I can still use the capacity plus minus those error bounds with confidence, but it's going to be less capacity because the error bounds are bigger. If I've got a poor estimator and I don't have error bounds at all, as we'll see, some of the poor estimators that we're going to look at, they don't even give you error bounds, then we have to guess. So if I have an SOC estimate that's 50% plus or minus 5%, I know what to do with that. But if I have an SOC estimate that's 50% plus or minus 50%, which is obviously extreme and crazy, I don't know what to do with that. I don't know if I can charge a pack or discharge a pack or do anything because I could actually have that cell might actually be at 100%. It might be at 0%. I just don't know. So large error bounds or unknown error bounds cause me to operate in ignorance, and I'd rather not do that, especially with such an expensive, valuable resource as a battery pack in a vehicle. So this is, again, an argument for why you might want to have an accurate SOC estimator, and now we know that we also would like one that has error bounds on the estimate that are known. From the user perspective, we're interested in reliability. So poor estimators behave differently for different usage profiles. If I'm doing one thing, the estimator may give me great estimates just by random chance, but if I'm doing another thing, it may give me very poor estimates. And in fact, the estimate might jump around. So it may say, oh yeah, your SOC is 80%, 80%, 80%. Oh, no, 95%. And then all of a sudden, if I go from 80% to 95% quickly, all of a sudden the vehicle performance has to change to accommodate that very quickly rather than smoothly where I don't perceive it, but I'm going to perceive it. And that's going to cause a poor driving experience, and it's going to be unreliable ultimately as well. So we want to have a reliable, dependable kind of estimator. Density is another way of looking at performance. Either I can get the full amount of performance out of the battery pack, which may be more than the spec for the battery pack demands, which is the first thing we looked at, but the density requirement looks at it the opposite way and says, well, if I've got a spec on my battery pack, and if I can use that entire SOC range with confidence, then I can make a small battery pack with no margin. But if I don't have confidence in my SOC estimate, then I have to over-design, over-engineer my battery pack by putting in more cells in order to meet the specifications. The performance specifications will require a larger battery pack. So having a good SOC estimator allows a smaller battery pack, a lighter battery pack. All of these things are very important for many applications. And finally, economy. Smaller battery systems simply cost less. Warranty service on a reliable system costs less, and that's a big deal. So that's some motivation up front of why we're spending so much time in this course looking at the state estimation, particularly some methods that are computationally or mathematically a little challenging to understand the first time, although I promise you that after you work with them for a while, they become pretty second nature. At least that's my experience. We're spending time on this because it's important. It has dollars and cents payoff, it has usability payoff, it has lifetime safety payoff, all kinds of things like that. So we're going to start at the beginning, because since state of charge is perhaps the easiest state member of a battery cell to relate to, we're going to focus a lot of our attention on estimating state of charge in particular. And the better we understand, the more carefully we understand and define state of charge, the better we'll be able to make estimators of what state of charge is. We looked at this picture in Chapter 1, you may remember, so I'm repeating a little bit, reviewing a little bit, our definition of state of charge from an electrochemical perspective. When we looked at the chemistry of a cell, we said there's a bunch of particles in each electrode. And these particles were built of a crystalline lattice structure that had the kind of, maybe not unique, it's not the word I'm looking for, but the desirable property that they were able to absorb lithium just like a sponge can absorb water. And they could have no lithium in the structure at all, and it doesn't necessarily degrade the structure, or they could completely be packed. They could be completely saturated with lithium, and that doesn't really affect the structure at all in many cases, or at least there's some range of lithium saturation, lithium usage that has no impact on this structure and can be used to store lithium in one of the electrodes. And we called the amount of lithium, we normalized the amount of lithium in the electrodes by using concentration ideas. So we talked about a concentration equals the number of moles divided by the volume. So number of moles per lithium divided by volume of material that the lithium could occupy. And in these crystal structures, it's possible to figure out theoretically what is the maximum concentration of lithium just by looking at the atomic structure and so forth, and knowing the density of the material. You can actually work this out. So CS max is a theoretical number where every possible vacancy that could hold a lithium atom is in fact holding a lithium atom. CS average says that, well, I might have lithium distributed maybe around the outside of the particle because I've recently been pushing lithium in, but maybe the inside is completely empty. So it's not the surface concentration of lithium that's important for defining a state of charge, but it's the average concentration. Or you could even think about it as a total amount, the total amount of lithium in one electrode versus the other inside the solid particles could be used as a basis for state of charge. But here we use the idea of concentration. So we defined a variable, we called it stoichiometry, the stoichiometric operating point of an electrode, as theta being CS average, the concentration of lithium in the solid on average in an electrode, divided by CS max. And that gives us a unitless number between 0 and 1. So 0 is down here on this picture where there is absolutely no lithium whatsoever in the electrode, in the solid particles of the electrode. And CS max is when every single available location that could hold a lithium is right now holding lithium. In practice, we never charge, if you will, a particle all the way up to CS max. because that tends to introduce stresses and strains and tends to approach some limits of chemical side reactions that causes side reactions to happen. And we'll talk a little bit more about that in the next chapter and in chapter 7 very, very briefly. But we tend not to use the entire possible range of lithium in the structure, and we back off a little bit for purposes of longevity and safety. And we define, and this is a definition, this is a design choice, it's not something theoretic, but as a design choice, we choose a value that we call theta 100%, which is the constant, well, it's the normalized concentration, it's the stoichiometry when I have charged the cell to what I am going to call the fully charged point. I could put more in. There's still some margin here. This is why it's possible to overcharge a battery cell, is because it's not because, well, when a battery cell is at 100% state of charge, that doesn't mean that there's no room for more charge. It just means that's my designed operating point when the battery pack is full. When I call it full, in fact, it could be more full, but there we start to introduce lifetime considerations and safety considerations if we do so. So theta 100% is not 1. Theta 100% is less than 1, but it's my design point for a fully charged cell. Similarly, for the bottom side, I define a theta 0%, and this is, again, a design choice. And it's usually not, and maybe I'll say never, it's not never 0. It's different from 0. This is why it's possible to over-discharge a battery pack, is because even when the cell is notionally at 0% SOC, there's still lithium that I could remove from the, I could move from one electrode to the other. I can still discharge more. It's just that if I do discharge more, it's going to cause a safety issue or a lifetime issue. So when we're thinking about state of charge for a cell, we're thinking about operating in this range, which is a smaller range than this range. This is why, if you go back and re-listen to some of the lectures from 5710 from the previous course, I tried to be careful to talk about an electrode state of charge versus a cell state of charge. This is the electrode state of charge, and this is the cell state of charge over there. The cell state of charge is over a more compact region. The picture is notionally drawn for the negative electrode. We understand that lithium moves between the negative electrode and the positive electrode back and forth. So for a positive electrode, I would actually have theta 100% being smaller than theta 0%, because as I charge a battery cell, this is going up and that is going down. The electrode SOC is going down while the cell SOC is going up. And while I discharge, this SOC is going down, but this electrode SOC is going up. And since the electrode SOC is the one that is moving in the same direction as the cell SOC for the negative electrode, I usually think of state of charge as being measured based on the negative electrode, although we can measure it based on the positive electrode also. We just have to be careful with our signs of our equations to make sure we end up with the right value that we're desiring. So with that background, cell state of charge is our familiar variable Z sub k, is theta sub k. It's the present stoichiometry of the electrode. It's the present CS average divided by CS max of the electrode, minus the theta 0% divided by theta 100% minus theta 0%. And if you look at that carefully, you'll see that Zk can range between 0 and 1 when theta k goes between theta 0% and theta 100%. And that even works for the positive electrode when the signs of theta 100 and theta 0, when theta 100 is less than theta 0, you're just going to find that this here is always negative and this here is always negative, in which case I end up with a positive result. So it all works out. So again, there's no direct way to measure state of charge because there's no direct way to measure these concentrations that would allow us to calculate the state of charge. So we have to infer or estimate state of charge using measurements of cell terminal voltage. and cell current. Now I stressed terminal voltage because terminal voltage is the voltage under load. It's different from open circuit voltage, which is the voltage when the cell is allowed to rest and come to complete equilibrium. We've seen curves last course of open circuit voltage versus SOC. It might look something like this. And if I was able to correctly, accurately determine open circuit voltage, SOC is easy. I just take the open circuit voltage and I come over here and I go down there, and I use this table, I use this relationship, whether it's a table or an equation or whatever, I use it to be able to determine the state of charge. However, the terminal voltage is different from the open circuit voltage. Terminal voltage we've seen looks like open circuit voltage, state of charge, and then I've got plus hysteresis, and then I've got minus diffusion voltages, minus IK times R0 in our equivalent circuit model. So unless this is negligible, and unless these have decayed to equilibrium, this relationship does not hold. Terminal voltage is not equal to open circuit voltage unless hysteresis is negligible, which really happens only at warm temperatures. Cold temperatures, hysteresis can be quite large, and unless the cell has rested for a long period of time. So voltage by itself is a pretty unreliable way of estimating state of charge, and we'll look at that in the next sections as we look at some poor methods to estimate state of charge. But it's useful to know, but it's not on its own reliable. So how can we know the true state of charge to evaluate our estimators? How can we know true state of charge for any purpose? This is kind of an interesting philosophical question. We're going to come up with estimators that give us some value for state of charge. It might say, oh, I think the state of charge of the cell is 58% right now. Well, how do you know if it's right? Even in the ideal situation, even when you've got a fully equipped laboratory, how can you know state of charge if you can't measure it? So we end up saying, well, we can never really know the truth for sure, but there will be ways to do some cell testing in the laboratory where we can get quite accurate calculations of state of charge from the lab test that we would not be able to make with such accuracy in an actual application. And so we will use the following definitions, hopefully to help us understand the problem better, but also we will use them to calibrate our laboratory tests to come up with the truth of what SOC really is against which to compare the estimates that we come up with. So these estimates may seem routine and boring, but they are important. Otherwise, we don't know if we're talking about the same thing when we mention the same term. So let's start out with, what do we mean by a cell being fully charged? And I say that for this course, we'll define a cell to be fully charged when its open circuit voltage, not its terminal voltage, but its at-rest open circuit voltage reaches some VH, H for high, VH as a function of temperature T, and this is a manufacturer specified voltage that might be a function of temperature. Hysteresis is a problem. We'd like to be able to eliminate hysteresis as much as possible, otherwise this is going to mess with us. And there were some ways that we talked about doing so way back in Chapter 2 of the previous course, using dither signals. I don't know if you remember that, and it's not really that critical here, but just have that in your mind if you're making cell tests yourself to fully charge a cell, is how do I know that its open circuit voltage has reached this as opposed to its open circuit voltage plus hysteresis, or its open circuit voltage plus some other terms from diffusion or whatever. So for example, the high voltage for a lithium manganese oxide cell at 25 degrees Celsius is often specified to be about 4.2 volts, just to have a number in mind. And for a lithium iron phosphate cell, it's often somewhere around 3.6 volts. Now this definition is a precise, accurate definition. How do we achieve it in practice? So a common method to bring a cell to a fully charged state is to charge the cell with some constant current until the measured terminal voltage reaches this maximum voltage. And then we hold the cell at that maximum voltage, at that constant voltage, until the charging current becomes infinitesimal. This is constant current, constant voltage charging, and we looked at that at the end of the last chapter. This is what's almost always done in a laboratory to bring a cell to a fully charged state. And this is going to be, when the current becomes infinitesimal, that means the diffusion currents inside the cell are infinitesimal and the IR drop is infinitesimal, and all I'm left with is OCV plus hysteresis. Now, hysteresis at warm temperatures may still be small, and it may be, you might just consider it negligible, and in many cases people do. If you don't consider it negligible, if you really need to be able to combat this hysteresis to truly achieve open circuit voltage equal to your maximum voltage, then you will need to execute some kind of dithering back and forth of the voltage around this Vmax set point to try to get that hysteresis loop to collapse to zero. And so the dithering we talked about, chapter 2 of the last course, is able to accomplish that in my experience. We define the state of charge of a fully charged cell to be 100%. So this is the connection. Why do we need to know if a cell is fully charged? Because if I can achieve that state in a laboratory setting, then I know that that cell is at a state of charge of 100%. It allows me to calibrate a cell test at the 100% state of charge point. We have a similar definition here for a cell being fully discharged. We say the cell is fully discharged when its open circuit voltage reaches a low voltage, V sub L of T. Again, a manufacturer specified voltage that might be a function of temperature. So V sub L at 25 degrees for a lithium manganese oxide cell is often something like 3.0 volts, and maybe it's about 2.0 volts for lithium iron phosphate, just to give two examples. Again, that is a purely reasonable, good definition of being fully discharged. How do I achieve that in practice? This next bullet tells about how to do a lab test that at least approximates it, and it's exactly the same idea that we discussed for charging a cell. We discharge by executing a constant current discharge profile until the terminal voltage hits the minimum voltage, and then we follow by a constant voltage profile. We hold the voltage until the discharge current becomes infinitesimal, and that again means that my diffusion voltages and my IR ohmic drop becomes almost zero, so that all that's left is hysteresis plus OCV. If hysteresis is considered negligible, then it's OCV is equal to my limit, I'm done. Or I can execute some kind of a dither step with current or voltage to try to make that hysteresis collapse to zero. And again, I refer you back to the previous course notes on that and the course text on that. In any case, the notation or the notion of being fully discharged is important because we define the state of charge of a fully discharged cell to be 0%. That's the connection. So when I do a laboratory test, what I'm going to do is I'm going to probably fully charge the cell before I do the test using a calibrated lab procedure that I know from a lot of working on it, it causes the cell to be fully charged. So this procedure, in my case, when I do this in my lab, I put the cell in a thermal chamber, I turn the thermal chamber on to the desired test temperature, I let the cell remain in that chamber for at least 2 hours, resting, doing nothing, so that the temperature is fully in equilibrium inside of that cell. Then I slowly, usually maybe a C/2 kind of rate, charge this cell to the maximum voltage for that temperature, do the constant current and constant voltage down to some minimum rate. For a precise lab test, I might do C/100 to get as close as possible to being at that desired that voltage, and then I will execute a sequence of dither steps. And in my case, I dither over the course of several hours, maybe 4 hours of these chirp signals that we talked about, of decreasing and increasing frequencies. And at that point, the cell is considered to be fully charged at 100%. So to fully charge a cell for a very precise lab test takes on the order of 1 business day. It's not a fast process. This is not what you would do in practice if you just drive your vehicle into the fast charge station and you plug it in and you're there for 15 minutes and then you take off. We're talking about something you don't have the luxury to do in real life, but this is a luxury that we have in a laboratory if I want a data set where I can calibrate the state of charge of at least 1 point. And that's what we do here. By the way, we know if we've achieved that if we disconnect the battery cell and let it rest for a period, maybe a few hours, and measure the voltage. If the voltage has not changed more than, a millivolt or so, then we are indeed at 100%. If the voltage collapses at all, we're not at 100%. We're probably close, but we're not there. Same with the fully discharged. Why is that important? Well, I fully charge my battery cell. I run the test. I get data of current and voltage and temperature. But where does the test end? I don't know. And so what I do is I take this cell and after running the test, I fully discharge this cell, because that allows me to have a second fully calibrated point of my test procedure. So I fully charge the cell, so I start at a calibrated 100%. I do whatever I do until I'm done, and I don't know exactly where I am right there. But then I fully discharge a cell, and so I've got a calibrated 0 point. And using the high precision, high accuracy sensors we have in the laboratory, which are much higher accuracy than you would expect in a vehicle or an application, I can accumulate ampere hours over time by integrating how much went into the cell, and I can determine then what is the capacity of the cell, which is what we talk about next, from the total number of ampere hours from this point to this point, and we can determine a state of charge as well, as we'll look at the end of this section. So the methods that we talk about here rely on a fully charged point. They rely on a fully discharged point for a laboratory setting. Can't reproduce that in the application, but that's okay. The total capacity of a cell is the quantity of charge that is removed from a cell when it is brought from a fully charged state to a fully discharged state. The metric unit for charge is coulombs, so strictly speaking we should measure capacity in coulombs, but it's a very awkward unit to use because the numbers tend to be so bizarre. So it's much more common in practice to use ampere hours or milliampere hours to measure the capacity of a battery cell. So we have to divide by 3600, in other words, to get into ampere hours, or 3.6 to get into milliampere hours. The total capacity of a cell is not a fixed quantity. We'd like to think it is, but it generally decays slowly over time as the cell degrades. So at any point in time, the capacity is not a function of temperature, it's not a function of state of charge, it's not a function of anything. The capacity, if you go back and you think about it, is going to be delta theta times CS max. It's the window of concentration that I can use inside of the electrode itself. And that has to be normalized into ampere hours, and we saw how to do it last semester. We have to multiply by epsilon SAL over 3600 times F to get it into ampere hours, but it's proportional to CS max. The capacity, if you want to think about what does capacity really mean, it means how many vacancies are there in the structure of the electrode that I can use to put lithium in or take lithium out of. So that, you think about it, it's just the number of rooms in your hotel. If your electrode is a hotel, how many rooms are there? So capacity degrades only slowly over time because of cell degradation. Your hotel is falling apart, or for other reasons that we can think of later in the course. But capacity doesn't depend on how quickly I put people in or take people out of a hotel. There's a certain fixed number of rooms. There may be other problems if I try to put people in too quickly, but it's not a capacity problem. And people mix this up all the time. And they use the term capacity to mean, at least 3 different things, maybe even more. So the type of capacity we care about in this course is total capacity, and that's what we just looked at. But a type of capacity that many people think about and many people talk about, and maybe it's even the default in most people's conversations, is what I call the discharge capacity of a cell. And I'm going to denote it as a Q with a subscript, where the subscript is rate. So the rate might be 1C or 2C or 3C. It's the rate at which you're charging or discharging a cell. And this is a quantity that depends on how quickly you are taking charge out of a cell. Because look how this is defined. The discharge capacity of a cell is the quantity of charge removed from a cell as it's discharged at a constant rate from a fully charged state, so the same start condition, but until its terminal voltage reaches VL, not until it's fully discharged. The terminal voltage, V equals OCV plus hysteresis minus diffusion minus IR. Let's at least pick on IR, if nothing else. If current is big and R is non-zero, then V is going to encounter VL far before OCV encounters its limit because of this IR term here. So the discharge capacity of a cell is how much charge can I get out at a specific rate before I hit a voltage limit. It's not the total amount. The SOC is not 0 at the end of this test. The state of charge is still above 0. So that's why these are different ways of thinking about capacity. So because the discharge capacity is determined based on loaded terminal voltage instead of open circuit voltage, it strongly depends on the cell's internal resistance, R, 0. The resistance is itself a function of rate and a function of temperature, and so this whole discharge capacity is a function of rate, temperature. So if you look at a data sheet for a cell, people tend to plot discharge curves. And this might be the C over 2 discharge curve, this is the 1C, and this is the 2C discharge curve. And they'll say this is in ampere hours and this is voltage. And they'll say, oh, well, my cell has a 1C discharge capacity of 1 amp hour that has a C over 2 discharge capacity of 1.5 amp hours, and this is 0.8 amp hours. I don't know, the numbers don't matter. But you look at that data sheet and you say, oh, capacity depends on rate. No, it doesn't. Discharge capacity depends on rate, but not total capacity. This cell here, that condition, when I hit the minimum voltage, I have not yet hit 0% SOC, nor have I here, nor have I here. It's only if I discharge at an infinitesimally small rate, a C over infinity rate, whatever that is. Obviously, it would take a long time to do. But this here is your total capacity Q, assuming hysteresis is negligible. So hopefully that becomes clear, and you can read a data sheet and understand that what they are talking about when they talk about capacity is different from what we're talking about here when we're talking about total capacity. I think I've said all of that. Discharge capacity is also something that will degrade as the cell decays, as its cell ages, because the maximum available storage capability of lithium goes down, and so the discharge capacity has to go down also. In fact, the discharge capacity will probably go down more quickly because it also depends on resistance, and resistance increases over time. Okay, so we have total capacity and discharge capacity, quite different quantities. People tend to use the terms very loosely, so be careful to understand which term is most appropriate at any point in time. Nominal capacity is also different. Nominal capacity is simply the number that's printed on the side of your battery cell when you purchase it. It's whatever the manufacturer says the capacity is. So if I purchase 100 cells of the same type, they will all say the same capacity number on the side of the cell. Maybe it's 10 amp hours. But in fact, they will all have slightly different capacity due to manufacturing variations and variabilities and whatnot. So the nominal capacity is just kind of a number we use for rough back-of-envelope calculations to determine if a cell is going to meet our design needs. It's not anything specific about one particular cell that you might purchase. So it's usually intended to be representative of the 1C discharge rate, so Q sub 1C of some particular manufactured lot of cells when measured at room temperature. So nominal capacity is a constant value, it's just a number, but the nominal capacity is a number that represents on average the entire manufactured lot of cells of that type. It's different from being something that represents any one individual specific cell. So QNOM is not equal to Q1C, even at the beginning of life, and it's certainly not equal to Q either. It's like saying that a statistic cannot represent an individual. If you've taken a statistics course, and hopefully you have, you would understand what we mean by that. Okay, we're almost there. A fourth definition of capacity is residual capacity. The term is not used very often, but it can be. You can see it, so I'll bring it to mind here. It's the quantity of charge that would be removed if the cell were brought from its present state to a fully discharged state. It's how much usable charge is in the cell right now. So if the cell is fully charged, the residual capacity is the full capacity, the total capacity of the cell. If the cell is fully discharged right now, the residual capacity is 0. So residual capacity is time varying, indicating what is the status of this cell right now. Then the state of charge of a cell, electrochemically speaking, and using all of these definitions, is the ratio of the residual capacity to the total capacity. So it's resid over total. And if you follow these definitions through carefully, these definitions are consistent with what we have seen all along. With the differential equation, z dot equals minus eta of t, I of t over q, which we integrate to get this integral state of charge equation, and we convert to discrete time to get this discrete time state of charge equation. All of those are consistent. But we go back to our lab test result, and I'll come back here, right here. How do I know the state of charge in a lab test? Well, I can find the total capacity by adding together all of the ampere hours from the beginning calibrated point of 100% state of charge to the end calibrated point of 0 state of charge. And then I can find the residual capacity at any point in this test by integrating. Actually, the residual capacity would be integrating this from there to there. And so that's going to give me the resid capacity. And so at any point in the test, I find the residual capacity, I divide by total capacity, and that gives me state of charge for the test. When we talk about poor state of charge estimation algorithms, we'll talk about Coulomb counting. This is Coulomb counting in a laboratory, but it's a very calibrated Coulomb counting, and it's using very high precision calibrated sensors, and it's about the best we can do in a lab. In real life, there's huge problems doing Coulomb counting because I never calibrate that point, and my sensors may not be anywhere near as accurate as they are in a lab setting. So there's problems with Coulomb counting in practice, and we'll talk about that, but this is how you would do it in a lab setting. This has turned out to be a really long section. I didn't really expect it to be this long when I broke up the notes this way, so thank you for your attention through it. I believe these definitions will be helpful to you, and now we're ready to move on with the definitions and look at some preliminary simple state of charge estimation methods that we might consider using.